Good morning again. I'm continuing to discuss entropy with the black hole example. This one I'll do the universe as an example. I'll make the universe into a black hole, whether Mr. Carroll says it is or not. One way or another, the last day I had this done and I was defining information, okay? Shannon's information. And it works out that we're going to define it as a probability, with a log of a probability. So information is going to be defined to be the log of the probability of x, but wait, when I decided to consider an event whereby I won a lotto ticket, 1 out of 10 to the power of 6 tickets. That's the same as the probability being of winning is 10 to the power of minus 6. But wait a minute, I picked up a minus sign. We'll get rid of it. We'll define information as being negative the log of that, in which case we get a positive 6 as being the information associated with this statement. I won the lotto ticket. 1 ticket I bought out of 10 to the power of 6 tickets. My probability of winning was 1/1,000,000th. Okay? And the log of 1/1,000,000th is 10 to the power of 6 once I have a negative sign in there. So we have to have a negative sign. I misdefined the information. Okay, the next thing is entropy. So the information is defined to be the negative, the log of the probability of the event. Okay, so we'll get rid of this now and look at, that was the entropy of a black hole, by the way. And I adjusted this. This was an adjusted black hole entropy. Check the previous lecture. Now we look at Shannon's entropy. I've already done an example or two with Shannon's entropy. Check the last lecture to see the example. I'm just looking at the equation at the present moment in time. H is negative the sum of the possibilities I equals 1 to n of n cases of probability I of events x. I think it's got a negative sign in it as well. No. And I'm sticking with the base 2, okay? Now, what does this look like? Okay. It looks kind of like an expectation value. If we define this to be our quantity, and the probability summed up all the possible cases, that's like an expectation value, I think. What is expectation value? Let's see what it is. Okay, I'll do it by an example. Expectation value. There are 100 tickets printed to win $100. Okay, I buy all the tickets. How much will I win? How much do I expect to win? So that's my expectation value if I buy all the tickets. Okay, so I buy 50 tickets. What do I expect to win? Well, here's the way we do it. If I take this event to happen, let's say 100 million times, right? 100 million times 100 is 200 million hundreds, or whatever it is. Suppose this event happens many times. It's like tossing a coin 1,000,000 times. Half the time you'll expect it to be heads, unbiased, half the time tails. But you have to do it many times. You can't just rely on one event to get a heads or half a heads. Okay, so if I buy 1 ticket, I say 50 first. I expect to win $50, but you say, wait a minute, the prize is 100, you either get it or you don't. I'm saying if you do this many times, right? If I do this kind of a process, you know, every hour for every day over a year will expect to win, on average, $50 per event, right? Okay, because some days you'll win, some days you won't. Let's buy one ticket. I expect $1 and let's see where we're getting this from. I take the probability of occurrence times the amount and I get the expectation value. So the probability of winning times the amount is the expectation value, but up here, the amount is the amount of information, okay? In other words, the I. Each I is a log of the PI. So that's our Shannon entropy. Now for the black hole, no, I didn't do a log actually, we just took the area. Now A over LP squared we said was an N. Some very large number in the case of a black hole, also in the universe. And K, of course, is Boltzmann's constant. Let's get rid of this. Now we said that we don't have to consider the universe or a black hole or anything in its three-dimensional case, a big surface. No, it's sufficient to consider the disk. All information can be encoded on a disk, in this case here of radius pi r squared. That's why the factor of 4, in my view, creeps in here, although other people derive it by different steps. This is sufficient to say that the entropy is going to be given by dividing the Planck length squared, which is an area, so we take the Planck length and square it, and we get 2.56 meters squared, and I did that the last day. Let's work out the entropy for the universe. So all I need up here call this A0. All right? So all I have to work out is that. In a simplistic view of the universe, I could take the universe and give it a radius r and see how we can find that. Okay, we have we will say that at the horizon, all the galaxies are receding at a maximum speed of the speed of light. So at the RU, the speed of light is the recession speed, and c is HU. Now this is Hubble's law, and I've discussed that before. It means that the further you go away, the bigger your speeds are, and it's a straight line graph through the origin, right? So at some point, we're going to get C, here at the edge of the universe. Right? So, what is H? H is 70 kilometers approximately, measured to be 70 kilometers per second per megaparsec. But what's that in real words? I actually converted it. 1 parsec is 0.3086 by 10 to the power of 16 meters. So if I put 10 to the power of 6, kilometers per second per megaparsec, and put in this number for parsec, I'm going to get Hubble's constant as 2.3 times 10 to the power of minus 18. Now, Hubble's constant has the reciprocal units of time in SI units. So that's H. So, what is R? R is going to be C over H. And this is the H. Now the seconds cancel, and I'm going to get units of meters, and the units I get are 2.3. What do I get? .3, sorry. So the radius of the universe, if I assume this condition, is going to be 1.3 by 10 to the power of 23 seconds. So now I can find the pi r squared. Now A0 is 2.56 times 10 to the power of minus 70, and this is going to have units of joules per Kelvin. This and this will cancel out their units. Well, this is not right yet. Pi is dimensionless. Anyway, these are going to be the units. So if I work out all those things, I'm not going to go through it now because I did it already. Now I haven't worked out Boltzmann's constant factored into this yet. So I have to yet multiply by Boltzmann's constant. Or I could define, this is the information part, which I define as being the W. And this is going to be our N. In other words, the number of bits is 2 by 10 to the power of 122 bits. That's the information part. But let's get the entropy, the thermodynamic entropy. Is equal to. So I have to work out that calculation. Now it doesn't make sense to go further into these numbers because really the accuracy in there is very debatable. Okay, so if I take the 23 from this one, I get 99. So the entropy universe is approximately 1/3 of 10 to the power of 100 joules per Kelvin. So, you know, is that right? I don't know. I'm very open to the idea of redefining entropy for a black hole as this. Sorry. Would like to redefine entropy for the black hole as just being k log to the base 2 times our n. In other words, our W part, okay? So if I just wanted the log W, well, W is log Z, and Z is the big N here. If we did that, well, this is in the base 10, so I'd have to go and convert. But you get the picture, and we'll talk about that at another time. So we worked out the entropy for the sun, and we worked out the entropy for the universe, and then it just gets tedious thereafter. Okay? So, what will I tell you beyond that? Nothing much to do yet. I can show you something else. I'll leave that one out. That's enough for this talk.